Okay, welcome back. Now the demo I'm going to be talking about adiabatic processes. I'm going to show you an example of that. I have a shaving cream here. Basically, what is a shaving cream? Basically, it's a can that has gas in there that is dissolved in a liquid under very high pressure. When you exert a very high pressure in a gas, more of the gas can dissolve in the liquid and form a combination of a gas and a liquid, right, under very high pressure. So then when I press this button, the gas and the liquid together will expand. The gas that is dissolved in liquid and the liquid itself will expand together, right? And as they expand, they are expanding very rapidly in a process known as adiabatic. That means there's no exchange of heat between the gas and its surroundings. So the gas expands and it cools. And it turns from a liquid into a solid, foamy substance. And that is the technology that we use known as the shaving cream technology. You can also do this with this demo with a carbon dioxide fire extinguisher, which is basically a carbon dioxide in a gaseous form, right, under high pressure inside of the fire extinguisher. And then when you press on the fire extinguisher and you put it next, you collect that with a cloth, you will see that the carbon dioxide will expand, it will cool, and it will actually turn into dry ice. So both of these examples are examples of adiabatic expansion. So what is adiabatic expansion? Adiabatic expansion is when the heat into the gas, which is equal to change in the energy of the gas plus the work done by the gas, right? The heat into the gas is equal to 0. That means the gas, when it expands, it does work against the environment, and therefore the work that it does is positive. So the change in internal energy equals negative the work done by the gas, and therefore we find that the energy of the temperature of the gas will drop, and it might turn into a liquid. In the case of the carbon dioxide fire extinguisher, it will turn from a gas to a solid, right? It will turn into dry ice. So what is the PV diagram of an adiabatic expansion look like? Well, if this is V initial, P initial, right, the pressure and the volume will drop into some V final, right, and then this is P final, and the equation is that P initial, V initial to the gamma is equal to P final, V final to the gamma, right? The gamma factor depends on the ratio of the specific heat at constant pressure to the ratio of the specific heat at constant volume. And if the gas or if the liquid is a diatomic gas, then the gamma is equal to 1.40. This is 1.40 for diatomic. In the case of the carbon dioxide gas that is going to expand inside of a fire extinguisher, carbon dioxide is triatomic, right? So for triatomic, the value is 1.28. So we call this polyatomic. And then if the gas or substance is a monatomic substance, for monatomic it's 1.67. Okay, so let's say in the case of the shaving cream, let's say the liquid that is in there that has the dissolved gases, let's say it is diatomic. So then I press on it, right? It's under high pressure. I press on it. You see it's how it's turning into solid. It's expanding. You see it's forming a solid foamy substance, which then you can take and you can shave yourself. What a good technology, right? So it's expanding. The pressure inside is maybe something like 1.5 atmospheric pressure. It's higher than atmospheric pressure, but not necessarily that much higher. Let's assume it's 1.5 times atmospheric pressure, maybe twice atmospheric pressure. So my question is going to be, what's going to happen to the temperature of the material in there? So what is the initial temperature of the material in there? Right? The initial temperature of the material in there is the same as the room temperature outside because it comes into equilibrium with room temperature. So the initial temperature, let's say something like 300 Kelvin, right? So in 300 Kelvin, that substance is a liquid. Liquid and a gas together under high pressure, and the volume is a certain amount of volume, right? So what I want to calculate is what is going to be the final temperature, okay? So let's do this. If I'm assuming that the initial pressure inside of the can is 1.5 atmospheric pressure, then this one we should be able to solve for it. In other words, we don't know the ratio when you press that button, we don't know the ratio by which the volume is expanding, right? If the initial pressure is 1.5 atmospheric pressure, then we can actually solve for this ratio. By what factor is the final volume bigger than the initial volume? Okay? Now, if somebody told us the final volume is twice the initial volume, then we can go and solve what is the initial pressure inside of the can. So one of these things has to be an unknown, and then we can use the equation for an adiabatic expansion to calculate for it. So if we assume the initial pressure is 1.5 atmospheric pressure, we put here P atmosphere, then V initial to the gamma, then we can say here this is P final is P atmosphere, okay, and then V final to the gamma, right? And then we're going to cancel the P atmosphere, right? So then what's going to happen? 1.5 is equal to V final over V initial to the gamma, right? I can take the V initial down here. Then I can raise side, let's say the material in there is a diatomic molecule, right? So then we can say this is 1.40, right? Now I can raise both sides to the power 1 over 1.40, 1 over 1.40. Then I get here, this cancels, and then I get 1.5 to the power. So V final is equal to V initial 1.5 to the power 1 over 1.40. Okay? That tells me by what ratio the volume expands. Okay? Okay? So that would be the final volume with respect to the initial volume, 1.336 V initial. So if I want to draw this graph to scale, what would I do? So then I would say P atmosphere is here, P atmosphere, and then this one is 1.5 P atmosphere. So you go like this, and then half of it. So the final pressure should be here, right? That would be a good accurate graph. So this would be 1/2. Then you add on top of that, right? And then the initial volume, if this is the initial volume here, this is V initial. Okay? So the final volume would be what? 33% larger than the initial volume, right? So it go like this, about 30% would be like this. So V final would be about here. Okay? So the final volume would look like that. So the drop would be like this. From 1 atmosphere to 1.5, from 1.5 atmosphere to 1 atmosphere. Okay, goes like this. And so this is the final volume, this is the initial volume, right? So now if I assume the initial temperature is room temperature, which is a good assumption, and let's say the room temperature is 300 Kelvin, what will the final temperature be? So then I can calculate here, 273 Kelvin is 0 Celsius, so this is roughly about -6 Celsius. -6 Celsius. So if the temperature of the material drops from room temperature to -6, right? And if the material is, let's say, has a freezing and melting point of 0 Celsius, then of course it will turn into solid, right? So you could do similar kind of calculations, find out the carbon dioxide fire extinguisher, what is the pressure inside the fire extinguisher, right? And then the temperature inside will be room temperature, right? And then the gas of the fire extinguisher will expand. If you put a cloth to it, it will be similar like this. The gas will come out, and instead of turning into foam, it actually turns into dry ice carbon dioxide. So it goes literally from gas, instead of going down to a liquid, it goes from gas to a solid state, turns into dry ice. Okay, so this is a good illustration of adiabatic processes. Another example of an adiabatic process is the gas that is trapped inside of a marshmallow. Like we all love to go camping, right? We put a marshmallow and start cooking it, right? Start heating it, and we see the marshmallow rising. So that's also adiabatic process. The gas inside of the solid marshmallow is trapped in high pressure, right? So then when you start heating it, the gas starts to increase in size, right? And then after there's no space to go, the gas is released, right? And then the marshmallow comes back down to regular size. So that expansion is also an example of an adiabatic expansion, and it's the gas that is trapped inside of the marshmallow, solid marshmallow, okay? So you can see there's different processes that utilize an adiabatic process, okay? This is a very important process, and it's also used in the Otto cycle, which is the engine cycle. The isovolumic, adiabatic, isovolumic, and adiabatic, okay? Thank you very much.